Welcome to this lesson. We'll be treating hybridization and shapes of molecules. So let's go into the understanding. We've been hearing hybridization, hybridization. So now we'll be going into detail about what hybridization actually means and how it affects the shape of molecules. So first off, hybridization is a model that tries to explain the mixing of atomic orbitals to form new hybrid orbitals. So when you hear the word hybridization, it should just tell you, okay, you're trying to mix two orbitals to form two different orbitals to form a new orbital that is neither the first, that is neither completely the first two, but is a kind of hybrid of the first two. Is a combination of properties of the first two um, orbitals. So now these hybrid orbitals are used in bonding, that and they also describe the geometry and the bonding pattern of molecules in that particular atom. So this concept is essential in explaining the observed shapes of molecules. So let's head into the further description of what hybridization means. So as we can see here, we have three basic types of hybridization for basic level. We have three basic types of hybridization, but there are more than three. There are more than three. There are several types, not even just more than three. There are several types of hybridization, but for basic level, you'll be seeing just SP hybridization, SP2 hybridization, and SP3 hybridization. So there are also stuff like DSP3. There's also D2SP3. There's also other combinations where you would also have F, D, and S with P orbitals hybridizing to form new orbitals. So now let's see the three main types of hybrid. The main types of hybridization are SP, SP2, SP3, SP3D2, and SP3D orbitals. So they could also be variations of this SP3D and also SP3D2 or SP3D2 orbitals. So each of these they correspond to specific geometries. So for example, we have the SP3 hybridization always having a linear geometry, SP2 hybridization always having a trigonal planar geometry, and SP3 always having a tetrahedral geometry. So this is the reason why alkanes are said to be tetrahedral, because they have SP3 hybridization. So here are some of the shapes of molecules and their corresponding, some of the geometries rather of molecules and their corresponding hybridization. So when you see an sp3 hybridization or sp3 hybridized molecule, usually the shape would be linear. So the shape will be usually linear. So when you see an sp3 hybridized molecule, the shape is usually going to be tetrahedral. It's going to be tetrahedral. So also when you see an sp2d hybridized molecule, the shape would be square planar. The shape would be square planar. When you see an sp3d hybridized molecule, the shape will be trigonal bipyramidal. So when you see an sp2d2 molecule, the shape would be square pyramidal. When you also see an sp3d2 molecule, the shape would be octahedral. So it would be octahedral geometry. So here are some of the examples we can see by the extreme right. So in SP hybridization, I'm trying to explain these types of hybridization individually now. So we're focusing on SP, SP2, and SP3. In SP hybridization, we have one s orbital mixing with just one p orbital. So when we have in a particular molecule, we have one s orbital mixing with one p orbital, they would form a single orbital called the s. They will form two new orbitals, and these two new orbitals would no longer be called ordinary s or ordinary p. They will be called sp. It's just like as if it's a kind of union between these two orbitals, where the s orbital will no longer be purely s, to now be s and p. Then the p orbital will no longer be purely p, but instead it will now be s and p also. So this is what happens during sp hybridization. So in case of sp2 hybridization is when we have one s orbital hybridizing with two p orbitals, that's two different p orbitals, so forming three new orbitals that are neither s nor p orbitals. So these three new orbitals would have characteristics that are similar to s and p orbitals, but now with a ratio where they would have more p properties than s properties. So the s orbital will no longer be a complete s orbital, but instead it will be an s orbital. It will be an orbital with some level of s characteristics and more level of p characteristics. So while the p orbitals also will no longer be purely p orbitals, but they would have some characteristics of s orbitals. So when we have an sp3 hybridization molecule or hybridized molecule, we are having an s orbital being mixed with 3p orbitals. So the s orbital will no longer be purely s, but instead it will have tiny s properties and more p properties. The p orbitals will no longer be purely p, but they will have tiny s properties alongside their p properties. So this is how these kind of orbitals form, and they have characteristic bond angles. So for sp orbitals, they would have 180 bond angle. For sp2 orbitals, they will have 120 bond angle, and for sp3 orbitals, they would have 109.5 bond angles. So hybridization and shape of molecules. So hybridization helps to explain why molecules have particular shapes. For example, methane, we have a tetrahedral shape, which is what I've explained earlier, because it has an sp3 hybridization. Ethene has a linear shape because it is sp2 hybridized, and so on. So the concept also applies to atoms with lone pair of electrons, like ammonia. Ammonia, we have nitrogen being bonded to three hydrogen atoms, but it also has a lone pair of electrons. So this lone pair of electron will cause a kind of bending to the structure of this molecule. So, and also ammonia has hybridized a kind of hybridization that is going to give rise to a trigonal pyramidal shape. It has that kind of hybridization. So the same thing happens also in water molecule. Same thing happens in water molecule, and also the bending of water molecule is as a result of the presence of two lone pairs of electrons. So these lone pairs of electrons, as we were saying, and also the hybridization of the molecules are responsible for the shapes of these molecules. So now, molecular shapes are also influenced by the presence of multiple bonds and also electron delocalization. So this presence of multiple bonds also influence the shape of molecules. So, and also they can also alter the geometry slightly from the idealized shape predicted by hybridization alone. So when we have delocalized electrons or multiple bonds, so they can also affect the shape of a molecule. So initially I've been mentioning that hybridization affects the shape of molecule. I also said lone pair of electron also affects the shape of molecule. But also another characteristic that also affects molecular shape is presence of multiple bonds or the delocalization of electrons. So these things can also affect the shapes of molecules. So overall, hybridization is a vital concept that unifies the understanding of molecular shapes and also molecular bonding. So by combining orbital theory and Vesper's theory, that's the VSEPR theory, in line with hybridization, we can be able to get a complete picture of how the molecular structure of different molecules can appear in real sense. So in conclusion, hybridization provides a theoretical framework for understanding the geometry of molecules and allows chemists to predict the molecular behavior and interaction of molecules accurately. So that will be all for this lesson, and I'll be saying goodbye.